Welcome to day 8 of the macOS and iOS Security Internals Advent Calendar. Today we will just have a walkthrough through the XGNU source code so that you know what is basically where inside the kernel source code. So the macOS and iOS kernel is better known as the XGNU kernel. And the idea behind XGNU is that it's a hybrid kernel. It's hybrid because it contains 3 different parts. They are known as BSD, Mach, IOKit, and driver kit. So the first part, the BSD part, is much like any kind of Unix suite operating system like BSD or even Linux. And when you deal with entities, you reference them via identifier numbers like the user ID, the group ID, the process ID, the file descriptor, and so on. And when you call functions, you do this in the form of system calls as part of the kernel. So now we have the second part of the XGNU kernel. That's better known as Mach. So Mach does not use simple identifiers like user IDs, group IDs, PIDs, and file descriptors. Instead, Mach uses a concept of so-called Mach ports. Mach ports are something like a handle that's something similar to what you maybe see in Windows. So you basically have a handle to an object that is available via the kernel. So in the Mach part of the kernel, there's also the concept of something like system calls. It's called Mach traps. But in reality, Mach traps are basically just a smaller number of system calls that you use to basically manipulate Mach ports and also Mach messages. So because the real way you talk to the kernel and use the API in the Mach part of the kernel is basically via sending Mach messages. And specifically, the so-called Mach API is a set of Mach messages that basically provide all the API from the kernel to userland. The last part then of the kernel is what's known as IOKit or driver kit, and that's best described as a C++ driver interface. So you basically write drivers by inheriting these classes. And there is also a so-called IOKit API that allows you to manipulate these drivers from userland. And IOKit API is basically like a special form of Mach API. So it's basically implemented as a subsystem of the Mach API that is just responsible for IOKit. Okay, and that all said, when you download the XGNU source code from the internet and open the tarball, you will see that there's a bunch of subdirectories in the main directory, and then each of these directories has a bunch of more subdirectories. And let me just go through the most important here. Basically, there's a BSD subdirectory, and the name already gives it away. This is where the BSD part of the kernel is housing in. Then you have, of course, the IOKit directory, and this is basically where you find IOKit and driver kit. Then the last part is the Mach part of the kernel that is in the OSFMK directory, and that stands for Open Source Foundation Mach kernel. So these are where the 3 main kernel parts are located. And so if you are looking for a specific thing, you should go and look at the specific subdirectory. Okay, what are the other subdirectories? So the doc directory is where nowadays Apple dumps a bunch of documentation files in there. Sometimes they later will delete them in a newer version again. So it's sometimes a good idea to look at older releases of the kernel to find missing files here. But the basic idea is that they try to document certain things they do in the kernel, and their documentation is often quite good, at least better than what you will otherwise read any other places. So libkern is a library of functions that are used in various kernel parts. libsa and libsyscall, let's just ignore that. That has something to do with kernel extensions and system calls and blah. It's not so important for us right now. The security subdirectory is where the so-called Mach framework is implemented. This is something we will likely discuss in another day. Stun is the kernel address sanitizer. Platform expert is basically a bunch of platform-specific functions, like, for example, the handling of boot arguments and stuff like that. Yeah, and then the remaining are here tools and some other subdirectories. The other subdirectories not so important at all, and tools are various tools for debugging purposes. For example, when you do kernel debugging, all the LLDB macros that you can use during kernel debugging, they are basically implemented in this subdirectory. Okay, let's drill down into each of these major directories. So in the BSD directory, we have the BSM, the basic security module header files. By the way, there's a lot of these subdirectories, and sometimes they just contain basic header files, and so they are all skipped on these slides here. Then you have a crypto directory, which has a bunch of low-level crypto implementations like Blowfish, and basically you can see everything there. There's a bunch of other crypto stuff that is actually moved away from the BSD part of the kernel and into libkern. In /dev you have various devices, the source code for them. /kern you have the actual core of the BSD kernel, so that's basically stuff like the Mach file loader. You have the IPC, the BSD level IPC code, you have sockets, you have a bunch of system calls, you have the whole process, start, stop, fork, and exit, and so on. You have signaling in there, you have the KAuth authentication framework, and the sysctl implementation for variables that can be read from userland or modified from userland, and a bunch of stuff. Yeah, and then there's the libkern directory with a bunch of utility functions. We are not going into detail here. So then you have the miscellaneous file system directory. There's stuff like the bindfs, deadfs, defs, fdss, fs, fifofs, mockfs, nullfs, rootfs, specfs, and unionfs. All these special file system types, they are all stored in the miscfs directory. You will see that a bunch of other file systems are nowadays loaded via drivers, so they are not in the main kernel here. Then you have the /net directory. That's the basic networking base code. So this is not the IP version 4, IP version 6 stuff. This here is basically core networking base, like various packet filters like the Berkeley packet filter and the normal packet filter for firewalling. You have bridging code, routing code, Ethernet, PPP, TAN, NREF, VLAN, and a bunch of other stuff, all implemented in this one subdirectory. The now more interesting networking code is in the NetENet and NetENet 6. This is the IP version 4 and IP version 6 networking. You will find all the normal protocols and stuff in there, like RBOOTP, DHCP, ICMP, TCP, UDP, and all this kind of stuff you will find in there in the version 4 and the version 6 code. Of course, you find IP versions, the IPsec in there, and stuff like that. So there's more stuff. There's like the net key. You have the NFS for network file system. You have the PGO, which is the profile runtime. You have the kernel auditing code. You have the Skywalk subsystem. You have code that converts between Mach exceptions and Unix signals. You have the virtual file system layer. That's basically the layer between the userland executing a system call and the actual real file system. So there's a layer in between. That's the virtual file system layer. You have the virtual memory code of shared memory, the paging code, and stuff like that. Okay, so that's all the BSD part of the kernel. Let's move on. IOKit. So IOKit is also containing a bunch of subdirectories. First of all, there's this BSD dev directory. That's basically a bunch of stuff between IOKit and BSD part of the kernel. And then the most important directory is for sure the /kernel directory. That's where all the low-level IOKit core functions are basically implemented in C++. And then nowadays you have also a driver kit directory, which basically contains all the interfaces for classes that you can make use of in driver kit. The families directory is just like stuff like there's a watchdog timer driver and there's an NVRAM driver, so that you can make use of them and inherit from them and stuff like that. So then we have the whole thing of libkern. Libkern is a bunch of helper directories. So first there's the C++ directory. That's basically a C++ base class implementation, like for data object, like OS data, OS string, OS number, and all these kind of container objects for data objects in the kernel. You have the crypto library, you have some stuff for atomic operations, you have the kernel modules start and stop functions, you have the kernel extension loader, you have some network address parsing code, you have some logging functions, some fake object code, support for block functions and stuff like that. You have a standard IO directory that only has scanf in there. You have a bunch of machine-specific code for i368, x86-64, ARM and ARM64 code. You have basic functions to manipulate UUIDs. You have the zlib compression algorithm. Yes, and that's basically the libkern. And now we can get to the Mach part of the kernel, which is basically a bunch of directories. First of all, for all the different CPU architectures that exist, there's a platform-specific implementation for many functions, like ARM, ARM64, i368, and x86-64. And then you have a bunch of stuff that resolves around different Mach subsystems, like ATM, bank, the pager, the GSSD, the TextD. Yeah, and then you have stuff like the console, some core crypto code, device management for support of IOKit, and then basically there's the stuff that is not on the slides. There's a lot of interface code now where just the interface is defined, but the actual code is not in the kernel or Apple internal, basically. Like for example AMFI and core trust and stuff like that. So, and then we have other kind of code in the Mach part of the kernel, like IPC. which is very important because in Mach part everything is about messages and sending it between tasks and so on. So that's IPC code. We have KDP, which is the kernel debugger. Then the core of the Mach kernel is in /kern. This is also where you find stuff like the zone allocator, which is basically the most used heap in the kernel. You have the perf code for kernel performance counting. You have PMC for performance monitors and counters. You have the Mach directory, which defines all the Mach API interface. You have the kernel random number generator. You have some code for user space notifications and the virtual memory subsystem as part of Mach. Yeah, all of that is part of the Mach. And again, if you're looking for certain things, you know exactly where to look from these subdirectories. Yeah, and stuff like the security directory don't need to look into more details because it's just like one main directory mostly. But the platform expert is maybe interesting. So the platform expert is basically split up in two things. You have on the one hand, you have the so-called platform expert generic routines, and then you have the platform expert machine specific code. So the best thing to explain this is imagine kernel boot arguments. So there's one generic way how you pass boot arguments. So that code would be in the gen directory, and then for every different platform you maybe have a different way how to retrieve the boot args from the NVRAM or wherever they are coming from. And this is basically then platform and machine specific code. Also the device tree handling and stuff like that is basically platform expert generic code. Yeah, and that's the walkthrough through the actual directories in the kernel source code. Now let's have a look into some kernel code. I will show you where you can find the system calls, the Mach traps and stuff like that. So I just opened the most recent version of the XGNU source code that is released by Apple. And as you can see here, these are the directories that I mentioned earlier. And I opened the readme.md. And as you can see, this is explaining a little bit. It even also tells you a little bit about what is in what directory and so on. And yeah, it also tells you a little bit how you can build a kernel and stuff like that, which works to some degree basically. Yeah, but now let's have a look into stuff like where are system calls defined. So the easiest way to find system calls is you go into the VSD directory, and there is a file called syscalls. Sorry, it's in BSD. I need to close all of this. It's in BSD/kern, and there's a file called syscalls.master here. And this file basically defines all the different system calls that exist in this specific version. So for example, when we go through the very end, we can see these are the most recent system calls that were added to the system, like ungraphed DMG and proc info extended ID and graph DMG, and there's a bunch of these things. Shared region map and slide 2 NP. This is the one that I mentioned earlier, since iOS 15 for mapping the build child cage, and a bunch of other stuff. And when you look at these system calls, you will see, oh, they have actually like a bunch of parameters for each of the system calls. and then you might be motivated to search for the system call source code like this here. And what will happen then is that when you go through the actual system call, you will see that the prototype here does not match at all what you were expecting. And the reason for this is that every system call internally is called via a dispatcher function, which is called Unix_syscall. And this dispatcher calls all system calls with 3 arguments. The first argument is the process that triggered the system call. The third argument is the pointer to the return value. And then the middle argument is a UAP pointer, which basically points to a structure that contains all the arguments for the specific system call. And these structures, they are nowhere defined. In reality, what happens is during compilation, these structures will automatically be created from the syscall's master file, so that then they contain all the parameters to the actual functions. So here, for example, you see that the files count is coming from UAP and the mappings count is coming from UAP, and so on. Basically, that is the idea here. Yeah, this is how you find the system calls inside the XNU. Yeah, so that's what I said. These are the system calls. Now let's have a look at the next part, which would be the Mach traps. So Mach traps come from a table called Mach traps. And when you search for it, you will at some point find the table inside the source code. Let's see. No, actually, let's find Mach trap table. Yeah, here we have Mach trap table. And it should be defined somewhere here. Let's search for it. Here it is. So the file is called syscalls sw.c. It's in the Mach part of the kernel. And as you can see here, it defines the Mach trap table, and it has 128 entries. And when you look at them, most of them are actually invalid. They have no value. And then you see there's a bunch of those that are actually supported here, like some kernel APC, task build, process info, notify, and so on. So there's a bunch of traps here, but the majority are basically current invalid. And when you look for the actual code, for example, here thread gets special reply port, you can search for that, and you will find the implementation then here. And again, the code is called not with the same arguments, but with the structure that is defined here, which is all the arguments to the specific Mach trap. However, when we now look for this, you will actually find them implemented here. So you can actually see the actual arguments in the machtraps.h. So this time you can actually see the arguments, and they're not auto-generated during compile time. So that was the system calls and the Mach traps. Now comes the Mach API. So the Mach API is again one of those things that is automatically created during compile time. And we're not going into too much detail here, but I can show you how you find the Mach API. So it's inside the Mach part of the kernel. So we go to OSFMK. We have the Mach subdirectory. And now we have here the so-called defs files. So these def files is basically what defines the Mach API. So here you will see a subsystem is declared, and this is the arcade register Mach subsystem, and this is the base number. So the base numbers are important for numbering the routines. And here you can see the routine that exists in this subsystem is arcade register new up call, and then you see the parameters to the API. And in this case, because it only has one routine, the internal code number of this routine will be this here. When you look at something else like the Mach port devs, then you will see it defines the Mach port subsystem. 3200 is the first number, and then you can see it basically defines a bunch of routines. And the idea here is then again that the first routine gets this 3200, the next routine will be 3201, 3202, and so on and so on. And again, you see all the parameters that exist, and these parameters will then be automatically converted to the actual function that is required to deal with certain parameters. So for example, these here are ports, and so this will do automatic reference counting and stuff like this. If you want to see this in more detail, you will first have to compile the kernel, which we're not doing here today. So for now, just remember that when you have a Mach API, it's defined here via a routine, and then you can search for it, and you will find the actual implementation somewhere, like here. And this is now the C-level implementation of this Mach API. And when you look at the parameters, you will see the space, name, right, and the user reference. And when you look at this here, you see same thing, space, name, right, and the urefs as an out variable. And all of this is basically defined in the defs. And then during compile time, the so-called Mach generator is creating the glue code that in the end will call these C implementations and handle all the parameters hopefully correctly, and otherwise you would have run into a security problem. Yeah, so that's a very short intro on how you find Mach API that exists. Now let's have a look at IOKit. I told you earlier that IOKit basically also has an API, and this API is basically called IOKit API, but internally it is basically just a Mach API. So when we go to, there's a devices or device.dev file somewhere, or at least there used to be a device devs file somewhere. Let me find it. We search for iOS server and search for star.devs, and here we have it. So it's an OSFMK device devs. So this file here is basically specifying a subsystem that is IOKit. So this file here specifies all the IOKit API basically, and you can see here all the routines that exist for dealing with the IOKit subsystem. So one thing that you can learn now is that this is the actual definition of the API. The Mach generator will code the glue code for calling the API. But the actual API is implemented as part of IOKit. So let's close all these subdirectories here, and let's go to IOKit. Let's go to the kernel directory. So here we have the kernel directory, and now you need to know that the IOKit is usually provided via or many things are provided via the IO user client code. So there is actually a file called IO user client CPP, and when you look into this code, you see all the implementation of this IO user client CPP code, which is here you see a class called IO Mach port, and later you see the IO user client somewhere. And what you can also see is that when you scroll down, at some point the definition of the IO user client ends. Yeah, this is still IO user client here. IO user client. So, and yeah, here, no, it's still IO user client. Yes. And then finally you see this marker here, and then everything after this marker is basically the C code that implements the IOKit API. So iOS server version is an IOKit API, object get class, object get superclass. So when you look here, you will see iOS. Where was it? You have here the IO object get class, IO object conforms to IO iterator next. And when you now look here, you see the IO object get class, IO object get superclass, and get bundle identifier is something else, or conforms to is also something else. And here you have the iterator next, iterator reset, and these are basically the API that you see here. And yeah, so this is how you find all the code for all the IOKit API. And that's it for today. Have a great day and see you tomorrow.